There is a common assumption that a black hole acts like an unstoppable cosmic vacuum, actively reaching out to consume everything in its path. But if that pull is truly inescapable, we have to ask why it hasn't swallowed the entire universe. Why hasn't one grabbed all the planets by now? To test this, we can run a simple thought experiment. Imagine we replaced the sun in the center of our solar system with a black hole. The immediate instinct is that Earth would get sucked in. But it wouldn't. Earth would keep orbiting almost exactly the same way it does right now. That happens because a black hole follows the exact same rules of gravity as everything else. There is no magical mechanism pulling things across the universe. In physics, an object's gravitational pull is determined entirely by its mass. It doesn't matter what the object is made of or how large it is physically. This diagram compares two identical gravitational fields. If you swap a star for a black hole of the exact same mass, the surrounding field doesn't change at all. It isn't stronger, and it isn't weaker. Because the outward pull is identical, distant objects remain completely unaffected by the internal structure. They just orbit, exactly like they always have. So if the outward gravitational pull isn't stronger, what makes a black hole so dangerous? The danger is a result of compression. All that mass is packed into a microscopic point, which means you have to travel incredibly close to the center to actually experience the extreme effects of its gravity. The farther away you are from a mass, the weaker its pull. Black holes only pose a threat at highly specific, extremely close proximities. Getting close is only half the equation. The factor that dictates whether an object falls into a massive body or safely orbits it is speed. Looking at this diagram, you can see the outcome of insufficient speed. An object moving too slowly cannot resist the inward gravitational pull, and it falls directly into the center. But if an object has adequate speed, it resists the inward pull. It achieves a perfectly stable, repeating orbit around the object. If an object possesses extreme speed, its path will bend momentarily, but it carries enough momentum to escape the gravitational pull entirely. This dynamic helps define the event horizon. It is strictly a mathematical boundary where the required escape speed becomes faster than the speed of light. Black holes only trap objects that fail this speed threshold, and to fail it, an object must first cross that extremely close boundary. That leaves one final question. Why doesn't cosmic debris eventually lose its momentum and drift into these dense traps? The answer comes down to the true scale of space. The distances between celestial bodies are massive, vastly larger than human intuition accounts for. On top of that, the baseline state of the universe is high-velocity motion. Planets, stars, and galaxies are already moving incredibly fast. This combination of vast distance and pre-existing momentum creates stable planetary systems. Objects don't just randomly drift inward. The universe operates on a strict balance of spatial motion and gravitational pull. It is not being eaten. Right now, you are safely sitting on a fast-moving planet, proving that black holes don't hunt. They only wait for the rare objects that stray too close.